this lecture we will discuss elimination and its types. Mechanism of E2 elimination, more precisely called E2 anti-elimination. Evidences for E2 mechanism. Stereospecificity of E2 reaction. Stereoselectivity of E2 reaction. Regioselectivity of E2 reaction. E2 reactions in cyclohexane systems. Various examples based on E2 reactions. In the end we will discuss substrates where E2 Syn-elimination is the only possibility. Organic reactions where two atoms or groups are removed from the molecule to form a product is called elimination. Various types of elimination are 1. Elimination, which is also called alpha elimination. In this type of elimination both atoms or groups are lost from the same atom to give a carbene or a nitrane. For example, consider this molecule, in which X connected to B, leaves along with the bonding electron pair and the bonding pair between B and W, is retained on B to form a carbene or nitrane. Second type of elimination is 1,2 elimination, which is also called beta elimination. In this case atoms or groups are lost from the adjacent atoms to form a new double or triple bond. For example, in this molecule, leaving group X leaves along with bonding electron pair, and the bonding pair of W. A bond is retained between A and B to form a new pi bond. Atom B is attached to leaving group denoted as alpha and the atom A is directly connected to alpha position and is denoted as beta. Third type of elimination is called gamma elimination. In this case, atoms or groups are lost from atoms which are two or more than two bonds away. This usually leads to cyclization. For example, in this case, atoms are lost from carbons, which are two bonds away and leads to formation of a three-membered ring. Our lecture is based on beta elimination, also called as 1,2 elimination. This can be divided into two types. One type taking place in gas phase, also called as pyrolytic elimination. The other one largely taking place in solution. In case of reaction in solution, nucleophage or leaving group leaves along with the electron pair. The other atom or group leaves without its bonding pair, most often being hydrogen which is abstracted by a base. Beta elimination in solution mostly leads to the formation of new C-C double bond or C-C triple bond. This happens by any of the three types of mechanisms. E2, E1, or E1CB. We will discuss E2 mechanism first. Consider this molecule. X is leaving group here. This carbon must have hydrogen attached. This is called alpha carbon, and the immediately attached carbon is called as beta carbon, which has hydrogen attached. Base abstracts this beta proton, so that its bonding pair is retained to form a double bond between alpha and beta carbon. And at the same time, X leaves along with the bonding pair. This results in the formation of a new pi bond between the two carbons which lost the two atoms. It is obvious that, this is a one-step mechanism, two groups depart simultaneously, with proton being pulled off by a base. Therefore this only step must also be the rate-determining step. Therefore, mechanism must be kinetically second order. First order in substrate and first order in base. This is obvious, because rate-determining step involves both substrate and base. Since two molecules are involved in RDS, it is called E2 mechanism, elimination bimolecular. The base used may be neutral or negatively charged. We can write the rate equation as, rate equal to rate constant K, times substrate concentration, times base concentration. It means, doubling the substrate concentration doubles the rate. Likewise doubling the base concentration doubles the rate. Doubling both substrate and base concentration makes rate 4 times. If we plot rate against substrate concentration, we will get a straight line because rate is first order in substrate concentration. Similarly, if we plot rate against base concentration, we will get a straight line, as the rate is first order in base concentration. Among the evidences for E2 mechanisms are that the reaction must display the proper second-order kinetics. Since the RDS involves bond breaking of H from the substrate, therefore, substitution of H with isotope D should depict primary kinetic isotope effect. As an example, consider this substrate molecule with a leaving group bromine and beta hydrogens in red color. Upon treatment with ethoxide base, it gives alkene product by abstraction of one of the red beta hydrogens by base. Say the rate constant is Kh. If a similar molecule, wherein beta hydrogens are replaced with isotope deuterium, is treated with ethoxide base, to form similar type of alkene, by abstraction of beta deuterium. Say the rate constant here is Kd. The ratio of Kh and Kd was found to be 7.1, indicative of a primary isotope effect. This confirms that RDS involves bond breaking of H with substrate, confirming single-step E2 mechanism for this elimination. However, neither of these results alone could prove an E2 mechanism, since both are compatible with other mechanisms also, for example we will see in lecture on E1CB. The most compelling evidence for the E2 mechanism is found in stereochemical studies. E2 mechanism is stereospecific, which means stereochemistry of the product depends on the stereochemistry of the reactant. To understand this, let us write the substrate again. The base abstracts the beta proton, the bonding pair of proton and beta carbon moves to form a pi bond between beta and alpha carbon, and the leaving group leaves from alpha carbon along with bonding electron pair. For this, we can write a transition state like this, in which bonds being broken and bonds being formed are at intermediate stage and are shown in red dotted lines. Ultimately it leads to alkene product. If we focus on this transition state, we can see that 5 atoms involved in bond breaking and making, including the base, must lie in one plane. Which means that, alpha carbon and leaving group bonded to it, beta carbon and the proton bonded to it, as well as the base that is going to abstract this proton must lie in one plane. There are 2 ways for this to happen. One way is, this arrangement, in which H and X are trans with dihedral angle of 180 degrees. Another way is, this arrangement, in which H and X are cis to each other with a dihedral angle of 0 degrees. These are sawhorse projections, and can be converted into Newman projections for easy understanding of cis and anti-relationship of H and X. So, sawhorse can be drawn as Newman projection like this: the hydrogen on front carbon goes up, and X on back carbon, goes down with dihedral angle of 180 degrees. This is called anti-conformation. Similarly, this sawhorse can be drawn as Newman projection like this: both hydrogen on front, and X on back carbon goes up. And this is called eclipsed conformation. This one is called anti-coplanar arrangement. Whereas, this one is called Syn-coplanar arrangement. The anti-conformation is lower in energy because it is gauche anti-conformation. Whereas, this eclipsed is no doubt higher in energy than anti-conformation. We will now show the orbital diagram of concerted transition state in E2 reaction via anti-coplanar and Syn-coplanar pathways. In the anti-coplanar transition state, the CH and CX sigma bonds are coplanar, but on the opposite sides of the C-C bond. As the bonds break, the carbons change hybridization. The sp3 orbitals change to the parallel p orbitals, which then overlap to form the pi bond. This is staggered conformation, with base far away from the leaving group. In most cases, this transition state is lower in energy. In the Syn-coplanar transition state, the CH and CX sigma bonds are also coplanar, but on the same side of the C-C bond. As the bonds to hydrogen and leaving groups start to break, the hybridization at each carbon begins to change to sp2 and the remaining p orbitals start overlapping to form the pi bond. This is an eclipsed transition state. In addition to the higher energy resulting from eclipsing interactions, this transition state suffers from interferences between the attacking base and the leaving group. To abstract the proton, the base must approach quite close to the leaving group. In most cases, the leaving group is bulky and negatively charged, and the repulsion between the base and the leaving group raises the energy of the syn-coplanar transition state. Thus, out of these possible conformations, the anti-coplanar arrangement is most commonly preferred for E2 elimination. Thus, if beta carbon has one hydrogen only, then only one alkene can be obtained as product via anti-elimination. This is because there will be only one conformation, in which groups to be eliminated are anti. Thus the particular alkene isomer obtained as product depends on the structure of the reactant. This is the origin of stereospecificity in E2 elimination. Consider this molecule. Number the carbons 1 to 4. Absolute configuration of carbon 2 is S, and that of carbon 3 is also S. Therefore, we write this molecule as 2s3s. Upon elimination of HBr, we get this alkene, which certainly is E-alkene. Take this second isomer. The groups at carbon 3 are oriented to make this R. So this becomes 2s3r. Upon elimination of HBr, it gives alkene product, which is Z-alkene. We will understand the elimination mechanism of these two isomers to give different alkenes as products. Take this 2s3s isomer first. Convert this Fischer projection into Sawhorse projection. Remember that Fischer projection is always eclipsed, and we have converted it into exact eclipsed Sawhorse. If we see molecule from this side, we can write the Newman projection like this, in which groups on front carbon eclipse onto those on back carbon. For elimination to take place, leaving group and beta hydrogen must be anti. Therefore, we rotate the back carbon by 60 degrees, so that red bromine is exactly anti to red beta hydrogen. Now remove the molecule of HBr, we are left with this, in which phenyl and H is on one side, and two methyl groups on other side. We can draw the molecule exactly as it is. And we see similar priority groups are on opposite side of double bond to make it E-alkene. Now take another isomer designated as 2s3r. Convert it into Sawhorse projection. Remember, we converted eclipsed Fischer into exact eclipsed Sawhorse. Now we will convert it into exact eclipsed Newman projection. Red beta H and red alpha Br are exactly eclipsed in this conformation. So, we need 180 degrees rotation of one carbon to make the required anti-arrangement of Br and H for elimination. After such a rotation of back carbon, now H and Br are anti. Remove the HBr molecule. We now get this product, in which phenyl and methyl are on same side, and methyl and H are on same side. Redraw this molecule, and check out that this turns out to be Z-alkene, as the similar priority groups are on the same side across the double bond. Thus, the isomer with 2s3s configuration gives E-alkene as product after E2 elimination, and the isomer with 2s3r configuration gives Z-alkene as product after E2 elimination. Thus, this proves that E2 elimination is stereospecific. This stereospecificity is because of the requirement of anti-coplanar arrangement of groups being eliminated. Syn-elimination is not found to any significant extent, unless anti-elimination is greatly diminished by failure to achieve the 180-degree dihedral angle, for example in rigid systems. We will see some examples of this later. Remember that, this requirement of coplanarity is not entirely absolute. Small deviation from coplanarity can be tolerated. If proton and leaving group are nearly planar rather than being exactly coplanar, it is called periplanar. Thus, for E2 reaction, if the groups are not exactly anticoplanar, then anti-periplanar arrangement is sufficient for E2 elimination. For example, a dihedral angle of 178 to 179 degrees is okay. This requirement of anti-periplanar arrangement will determine the stereoisomerism of the product. In other words, we can say that, stereoisomeric product of an E2 reaction process depends on the configuration of the starting alkyl halide, hence making this stereospecific. Thus, this alkyl halide has required anti-arrangement of H and Br. Red-colored R1, on both carbons are on solid wedge, meaning they are on same side, and green-colored R2, on both carbons are on dash, meaning on the same side. Thus, elimination gives cis-alkene. Similarly, in this second example, H and Br has required anti-arrangement for E2 elimination. Red-colored R1, on both carbons is opposite, so are the green-colored R2, on both carbons. Thus, elimination gives trans-alkene. One important point to remember is that, the stereospecificity of an E2 reaction is only relevant when the beta position has only one proton. If beta position has two protons, then either of these two protons can be arranged anti to leaving group, so that stereoisomeric products will be obtained. Consider this alkyl halide. Beta carbon has two hydrogens, shown in red and green color. Red hydrogen is in anti-periplanar arrangement to bromine. Elimination gives this alkene with R1 and R2 on same side, as they are on solid wedge in starting alkyl halide. Now, we can rotate the C-C bond so that, green hydrogen is anti to bromine. Red hydrogen is now on solid wedge and R1 moves to dash. Elimination now gives this alkene product, in which R1 is anti to R2. In this case red H is eliminated, and in this case green H is eliminated. In such reactions, more stable isomeric alkene product will predominate, making this elimination a stereoselective reaction. Consider this alkyl halide, in which beta carbon has two hydrogens. It gives two products, trans-alkene and cis-alkene, trans being major and cis being minor. For better understanding, let us differentiate two beta hydrogen with red and green color. Trans-alkene is formed by removal of green H and cis-alkene is formed by removal of red H. To understand, let us draw the sawhorse projection of this flying wedge representation. Green H and Br are anti in this sawhorse projection. We can convert this into Newman projection, and see that green beta H is anti to bromine. This is more stable conformation and exactly as required for E2 elimination. After elimination of green H and Br, we get this product. Just stretch the front carbon with red H and ethyl group towards right, and put a double bond between two carbons. This is trans-alkene. To bring red beta hydrogen anti to bromine, we rotate the front carbon, so that now red H and Br are anti. We can convert this into Newman projection. It can be seen in this Newman projection that bromine is now anti to red beta hydrogen. After elimination of HBr we get this alkene, in which hydrogens on both carbons are on same side as are the methyl and ethyl group. This makes alkene have cis configuration. Now this conformation is gauche conformation, but compared to anti-conformation, it is less stable due to methyl and ethyl being apart only by 60 degrees dihedral angle, compared to 180 degrees dihedral angle in anti-conformation. Thus, trans-alkene is formed in major quantity as it is obtained from stable anti-conformation, and cis-alkene is formed in minor quantity as it is obtained from relatively less stable gauche conformation. Thus, this is an example of stereoselective E2 reaction. In many cases, E2 elimination reactions are regioselective and can produce more than one product. Consider this alkyl halide. There are two non-identical beta positions with respect to alpha carbon connected to leaving group bromine. So the double bond can form in two different regions of the molecule. This consideration is an example of regiochemistry, and the reaction is said to produce two different regiochemical outcomes. Both products are formed, but for reasons of molecular stability, the more substituted alkene is generally observed to be major product. This alkene is trisubstituted and is called Zaitsev product. Because this trend was first observed by Russian chemist Alexander M. Zaitsev. This is of course more stable. The minor product is disubstituted alkene and is called Hofmann product. This is less stable. The Zaitsev product being more stable is major product under normal conditions. Whereas the Hofmann product being less stable is major product only under special conditions. First is when base is bulky. Second, when leaving group is poor, such as fluoride anion, ammonium or sulfonium groups. Third is when there is steric hindrance at beta carbon. Fourth is when the Hofmann product is a conjugated alkene. Before going into the details of these conditions, let me tell you that Zaitsev product is major product in the above reaction, because product as well as transition state leading to the product is more stable, or we can say lower in energy. For example, consider this transition state leading to 2-butene and 1-butene. Because the transition state has an alkene-like structure, the transition state leading to the 2-butene is more stable than the transition state leading to 1-butene, for the same reasons that 2-butene is more stable than 1-butene. The more stable transition state allows 2-butene to be formed faster than 1-butene. In the energy profile diagram, you can clearly see that difference in the rate of formation of the two alkene products is not very great, so both products are formed, but the more stable alkene is the major product of elimination reaction. Now let us discuss the conditions that favor Hofmann product to be the major product. First is the use of bulky base. Consider the previous elimination reaction of 2-bromo-2-methylbutane. With ethoxide base, Zaitsev product is the major product, as we have just seen. However, with tertiary butoxide and higher alkoxides, the Hofmann product is found to be the major product. This clearly shows that the regiochemical outcome of an E2 reaction can often be controlled by carefully choosing the base. The reason for this change in regioselectivity is that a large, highly branched base preferentially attacks on the least sterically hindered beta hydrogen to form stable transition state. In this case, stability of transition state depends mainly on steric hindrance and not on the alkene character. Abstraction of less substituted beta hydrogen by bulky base gives less substituted Hofmann product as the major product. Second condition is when there is a poor leaving group like fluoride anion. In case of chloride, bromide and iodide leaving groups, the halogen starts to leave as soon as the base begins to remove the proton. Departure of the halogen and its bonding electrons prevents the buildup of negative charge on the carbon that is losing a proton, giving the transition state alkene character rather than carbanion character. Of the halogen ions, the fluoride ion is the strongest base, and hence very poor leaving group. So, when a base begins to remove a proton from the beta carbon of alkyl fluoride, the fluoride ion has less tendency to leave than do the other halide ions. As a result, negative charge develops on the beta carbon that is losing a proton, giving the transition state a carbanion character rather than an alkene character. This carbanion transition state is stabilized by the strong electron withdrawing group fluorine. Thus, transition state leading to Zaitsev product develops carbanion character on secondary carbon, which is less stable than the transition state leading to Hofmann product, where carbanion character develops on primary carbon, and is comparatively more stable. Thus, when alkyl fluoride is treated with methoxide base, Hofmann product is major product in this case, as it is formed from the more stable transition state. On the similar grounds, one can explain why the compounds having ammonium or sulfonium groups as leaving groups give Hofmann elimination. Third condition is crowding at beta carbon. If the beta carbon, whose abstraction by base would lead to Zaitsev product, is hindered, then the less hindered beta hydrogen leading to Hofmann product is preferred by base. For example, consider this alkyl bromide. It has two different beta hydrogens. These red beta hydrogens are bonded to secondary carbon, and these green beta hydrogens are bonded to primary carbon. These secondary beta hydrogens are sterically hindered, and their elimination with bromine gives this more substituted alkene. The elimination of less substituted green hydrogen with bromine gives this less substituted alkene. Thus crowding at secondary beta hydrogen forces the base to abstract primary beta hydrogen so that in the end, Hofmann product is the major product. The fourth condition favoring Hofmann product is when it is conjugated. If the substrate contains one or more double bonds, then that beta hydrogen is preferred by base, which leads to conjugation in the product. Consider this alkyl bromide substrate. It has secondary beta hydrogen shown in red color and tertiary beta hydrogen shown in green color. The abstraction of red hydrogen gives this less substituted alkene product, whereas abstraction of green hydrogen gives this more substituted alkene product. We call this Hofmann and this as Zaitsev product. In the Hofmann alkene new double bond is conjugated with phenyl ring, whereas in Zaitsev product new double bond is isolated. Therefore Hofmann product is major because it is conjugated and more stable product than Zaitsev product, which is an isolated alkene and hence less stable and minor product in this case. We will now discuss E2 elimination from cyclohexane derivatives. Cyclic compounds follow same rules for E2 elimination, as does elimination from acyclic compounds. That rule is, anti-periplanar arrangement of two substituents that are being eliminated. This requirement has special significance when dealing with substituted cyclohexanes. Consider this mono-substituted cyclohexane. The substituent X occupies equatorial position and is more stable conformation than when the ring flips to put the X substituent on axial position. In this case, there are two beta positions with two hydrogens each carbon having an axial and an equatorial hydrogen. It is obvious that none of the hydrogens on either beta carbons are anti-periplanar to CX. Only C-C bonds denoted as 1 and 2 are anti-periplanar to CX bond. But these C-C bonds can't be removed by base. Thus, E2 elimination is not possible in this conformation though being more stable. However, in this less stable conformation, axial CX is anti-periplanar to axial hydrogens on either beta carbons. Thus, E2 elimination is possible through this less stable conformation. Thus, for E2 elimination in cyclic compounds, leaving group and beta hydrogen must be in 1,2 diaxial arrangement. For example, in case of this chloro-cyclohexane. As said earlier, when chlorine is on equatorial position, it makes conformation more stable, but in this case none of the beta hydrogen are anti-periplanar to chlorine. Thus, base treatment of this conformation gives no E2 elimination. When ring flipping occurs to put chlorine on axial position, it makes this conformation less stable. Of the 4 beta hydrogens, encircled axial hydrogens on beta carbons are in desired anti-periplanar arrangement making E2 possible. We can show the mechanism of abstraction of axial beta hydrogen to form the cyclohexene product. Remember that, abstraction of axial hydrogen from either beta carbon gives the same product in this case. Consider this example, wherein trans-1-bromo-2-methylcyclohexane is treated with ethoxide base. 1,2-trans means 1,2 diaxial, or 1,2 diequatorial, out of which this diequatorial is more stable conformation. But, if we carefully observe this conformation, we see no anti-periplanar H on beta carbons, because bromine is equatorial. Thus E2 is not possible from this stable conformation. Ring flipping gives this diaxial conformation. With respect to bromine, 2 beta carbons are there. This beta carbon has only 1 hydrogen, which is equatorial and hence not anti-periplanar to axial bromine. This beta carbon has 2 hydrogens, 1 axial 1 equatorial. Only this axial hydrogen is anti-periplanar to bromine and is eliminated with bromine to form a double bond. Thus, this elimination doesn't follow the Zaitsev rule to form more substituted alkene. The reason is that, the elimination can occur only if the 2 substituents that are eliminated are in 1,2 diaxial arrangement. Thus, this axial hydrogen is eliminated even though it leads to formation of less substituted Hofmann product. We can write the product in planar form like this. And once you have understood how to apply the criteria and mechanism of elimination in substituted cyclohexane derivatives, you can write the product without going through chair conformations. For example, this beta carbon has methyl on dash, so the hydrogen must be on wedge. Likewise, this beta carbon has 2 hydrogens, one on wedge and other on dash. Since the bromine is on wedge, therefore, the two hydrogens shown on wedge are cis to bromine, and cannot be eliminated as per anti-periplanar requirement rule. Thus only this hydrogen on dash is trans and anti-periplanar to bromine, and can be abstracted by base to form this less substituted alkene product. So, the take-home message for E2 elimination of cyclohexane derivatives is that, atoms or groups to be eliminated must be in 1,2 diaxial trans arrangement, only then their orbitals are suitably oriented to overlap for the formation of pi bond. We will now discuss some factors that affect E2 reaction. First is structure of substrate. Remember that, branching at alpha and beta carbon increases the rate of E2 reaction. From this data, it is obvious that branching at alpha carbon increases the yield as well as rate of the E2 reaction. Based on this data, it is clear that reactivity of alkyl halides in E2 reactions is tertiary greater than secondary, which has greater reactivity than primary. Similarly, from this data, it is obvious that, branching at beta carbon increases the yield as well as rate of the E2 reaction. Thus, branching at alpha and beta carbon increases the E2 rate and slows down SN2 rate due to steric strain in SN2 reaction. In other words, we can say that, increasing branching at alpha and beta carbon increases E2 by SN2 ratio. Second factor is nature of the leaving group. In general, better the leaving group, higher is the rate for E2 reaction. Thus, from this data, it is clear that, when beta-phenyl halides are treated with sodium ethoxide in ethyl alcohol, the rate of the E2 reaction increases with the leaving power of the halogen atoms. Third factor is strength of the base used. With increasing basicity of the base added, the rate of E2 reaction increases. Among these bases, the order of basic strength is, amide higher than ethoxide, which has higher basicity than hydroxide. Thus, on a given substrate, rate of E2 reaction is same as above under identical conditions. Thus, rate of E2 reaction with given substrate under similar conditions is same as above order. Fourth factor is temperature. With increase in temperature, E2 by SN2 ratio increases. Thus, 2-bromopropane when treated with sodium hydroxide gives propene as elimination product. With increase in temperature you can see the rate increases. Fifth factor is nature of solvent. Increasing solvent polarity decreases E2 rate. This data is for elimination reaction of 2-bromopropane at 50 degrees Celsius with sodium hydroxide base. From this data, it is obvious that decreasing the polarity of solvent increases the E2 by SN2 ratio. Now we will practice some E2 reaction examples. Consider this cyclic substrate. With respect to chlorine substituent, there are 3 beta positions. This beta carbon doesn't have any hydrogen. Thus, only 2 types of beta hydrogens are available and hence 2 products will be formed. Removal of beta hydrogen from ring gives this cyclic alkene, and removal of beta hydrogen from exomethyl gives this exocyclic alkene. This alkene is more substituted and hence Zaitsev product. This alkene is less substituted and hence Hofmann product. Zaitsev product will be major and Hofmann minor product. Consider this alkyl halide treated with potassium tertiary butoxide base. This is a bulky base. Substrate has 3 beta positions. The 2 beta positions inside the cyclic ring are similar. Tertiary butoxide is sterically hindered base, and will therefore prefer less sterically hindered beta hydrogen for abstraction to form Hofmann product as major product. Thus, removal of any of the secondary beta hydrogens from the cyclic methylene gives this alkene with double bond inside the ring. While the removal of primary hydrogen of methyl gives this exocyclic alkene. This cyclic alkene is more substituted and this exocyclic is less substituted. Thus, this is the minor and this is the major product upon treatment with bulky base. Consider this beta-phenyl alkyl bromide substrate, treated with sodium methoxide base. Bromine is shown on dash, which means hydrogen at the alpha carbon has to be on wedge. Then this beta carbon has two hydrogens, one will be on wedge and other on dash. This hydrogen in cyan blue color is trans to bromine, therefore we can eliminate it without changing the position of any group. Let us show this double bond in cyan blue color. The product is trans, because phenyl and alkyl group are trans as are the white and red hydrogens. Since the molecule is free to rotate at room temperature and change conformations. During these rotations, bromine and red hydrogen will be trans to each other and elimination of red H and bromine can take place. We will see how such a rotation changes the configuration of molecule. So we will rotate alpha carbon so that bromine is now on solid wedge, hydrogen on this alpha carbon goes on dash and tertiary butyl group is now facing towards the side of phenyl ring. In this particular conformation, bromine and red hydrogen are trans and perfectly oriented for E2 elimination. This elimination of red H and Br gives this alkene in which pi bond is shown in red color. This molecule is cis, because phenyl and butyl group are on same side, as are the white and red hydrogen. For reasons of stability, trans is major product and cis alkene is minor product. Thus, this is an example of stereoselective E2 elimination. You can also use the Sawhorse or Newman projections to see the formation of these cis and trans products, as we have shown and discussed in earlier examples. Take this example. It is similar to previous one except that the beta hydrogen on wedge is replaced by methyl group. Bromine on dash means hydrogen is on wedge. On beta carbon, methyl on wedge means hydrogen is on dash. There is only one beta hydrogen and it is cis to bromine. Which means E2 is not possible in this conformation. To bring these trans, we will rotate, say, alpha carbon, so that bromine comes on solid wedge and thus anti-periplanar to cyan hydrogen on beta carbon. Once we rotate it, we get this conformation. Where bromine is now on solid wedge, hydrogen moves to dash and butyl group faces towards phenyl side. Now bromine and cyan blue hydrogen on beta carbon are trans to each other, and hence anti-periplanar, which means E2 is now possible in this conformation. Removing HBr gives this alkene, which is cis alkene and the only product possible because only one beta hydrogen is present in substrate. Thus, this is an example of stereospecific E2 reaction. Consider the elimination of this cyclic chloride. This is called methyl chloride. It has two beta carbons. This beta carbon has isopropyl group on wedge, therefore hydrogen must be on dash. Similarly, this beta carbon has two hydrogens. Let us put cyan blue hydrogen on wedge and red hydrogen on dash. This chlorine on alpha carbon is cis to this red beta hydrogen and this white hydrogen. Because both of these are also on dash. This chlorine on dash is trans to this cyan blue hydrogen on wedge. Therefore this will be eliminated on treatment with base to form this alkene product. Only one beta hydrogen is anti-periplanar to chlorine, therefore only one E2 product is possible. Take the similar isomeric molecule with chlorine cis to isopropyl group. Both shown on solid wedge here. This is called neomethyl chloride. Thus, hydrogen on this beta carbon must be on dash. The other beta carbon has two hydrogen, cyan blue shown on solid wedge and red one, shown on dash. This chlorine and this cyan blue hydrogen, both are on solid wedge, which means they are cis to each other. And hence it cannot be eliminated with chlorine. This red and white hydrogen on dash are trans to this chlorine on wedge, and hence, both can be eliminated with chlorine to form two different alkene products. Elimination of white hydrogen with chlorine gives this alkene, and that of red hydrogen gives this alkene. This is more substituted, and this is less substituted. This is Zaitsev product, and this is Hofmann product. Zaitsev product, of course, will be major, and Hofmann will be minor product. In this example, these isomeric cyclic bromides undergo elimination at different rate, first one undergoes elimination slower than second one. We will go into mechanistic details to find the reason for this different rate of elimination. Let us take the first one. Bromine and methyl are trans to each other at 1 and 4 position. 1,4 trans means 1,4 diaxial or diequatorial. In the chair conformation, we keep both on equatorial positions, because diequatorial is more stable conformation. In this diequatorial, bromine being on equatorial means that E2 is not possible. Upon ring flipping, both bromine and methyl are axial. Now that bromine is axial, it means E2 can occur in this conformation. There are 2 beta positions each having axial hydrogen, which can be eliminated by E2. But this methyl in axial position makes this less stable conformation. Elimination of either axial beta hydrogen shown in red gives this product and of course its enantiomer. Similarly, take the second molecule, in which bromine and methyl are cis to each other. 1,4 cis means, one substituent on axial and other on equatorial. Let us keep bromine equatorial and methyl axial. In this conformation, bromine being on equatorial position means that no beta H is anti-periplanar to it, hence E2 is not possible. Ring flipping puts bromine axial and methyl equatorial. Bromine is now axial, means that E2 can occur in this conformation, as it has axial hydrogen on 2 beta carbons. Moreover, this methyl is equatorial means that this conformation is relatively stable because methyl in essence is bigger than bromine. Now elimination of either red hydrogens will form this alkene product and its enantiomer. In the 1,4 trans isomer, the conformation from which elimination takes place has methyl axial, making it less stable, which is why elimination is slower than the beta elimination of 1,4 cis isomer, where the same methyl is equatorial, making it comparatively stable, which is why elimination is faster. Syn-elimination is less favorable than anti-elimination because the molecule must be in a higher energy eclipsed conformation for syn-elimination to occur. However, syn-elimination does occur in rigid molecules where the leaving group and the hydrogen are held in an eclipsed conformation. For example, the bicyclic compound shown here is very rigid. As can be seen in the Newman projection, down the C2-C3 bond, the Br and the D are eclipsed. Deuterium is used as a label to enable syn-elimination to be distinguished from anti-elimination. Syn-elimination results in the loss of the D and the Br, so the product contains no deuterium, whereas anti-elimination results in the loss of H and Br. So the product still contains the deuterium. In the presence of a strong base, 94% of the product alkene contains no deuterium and therefore has resulted from syn-elimination. Not much of the anti-elimination product is formed because the hydrogen on C3 and the bromine are not in an anti-relationship, the dihedral angle between them is 120 degrees. Thus, elimination of this hydrogen and the bromine occurs with poor orbital overlap at the early stages of the reaction. We will see more examples and conditions of syn-elimination in a separate lecture.